Hi, Nathan. Sorry, I didn't realize Kyle wasn't aware. I can moderate, but I'll
Great.
just get the Q&A at the end. I do have a few other things going on.
Absolutely. Yeah. Thank you.
Yeah, no problem.
Oh.
So yeah, everybody, welcome to the second lecture of week 7 of the MTV Nuclear Engineering Summer School. We're talking about fission this week. Just had a nice lecture yesterday on fission fragments from another PhD candidate, Kyle Baird. Today, we have PhD candidate Nathan Giha. He focuses on correlated multiplicity of fission and gamma rays and has completed some very interesting experiments and publications in collaboration with several national labs, most specifically Argonne National Laboratory. And yeah, we're lucky to have him for the lecture today. And I'll hand it off to you, Nathan.
All right. Thanks, Flynn. So today we're going to talk about the step that happens after the subject of Kyle's lecture from yesterday. And that is the neutrons and gamma rays that are emitted following fission or following scission, if you remember that term from yesterday. So just a brief refresher, if you think of a question, you can put it in the Q&A section on Zoom. And if there is a particular slide that's relevant to your question, please include the slide number. That will help. I can bring the slide back up while we're answering, and it'll be nice to have it in the backdrop. Flynn will let me know. It sounds like we'll do the Q&A session at the end. So let's go. Now, you saw this timeline yesterday on Kyle's slides, and he talked a lot about how fission is deformation, and it's deformation in the extreme. There are lots of nuclei that are deformed when they're excited. There are nuclei that are deformed when they're just in the ground state. But fission is what happens when the deformation is so much that it can't be deformed anymore, and it ends up splitting. So since I'm talking about the neutrons and gammas from fission today, we're not going to talk about the Sal decision, which is what Kyle talked about yesterday. And for the most part, we're not going to talk about beta delayed stuff, but there will be a little bit about that at the end. What we're primarily going to focus on is the prompt neutrons and prompt gammas. And you can see the kind of time frame here. But by the time a picosecond has passed after scission, we've pretty much emitted all of our neutrons. And then from then on to actually around a nanosecond after, although there are some that are longer lived, we've emitted most of our gammas. So it is pretty fast, not quite as fast as this, but it happens right after for the most part. So scission is what Kyle talked about yesterday, and I just want to remind you of the term since it'll be used again. Oops. Scission is the point in time at which the nucleus actually splits into two. So when it goes from this dumbbell shape to two distinct bodies, that is scission. And you might have seen this potential energy curve yesterday where the nucleus has to somehow get out of this potential energy well of its ground state to end up going to this super deformed shape. And in the process, there's a lot of kinetic energy released, around 160 MeV. Of course, that varies a lot. But we want to talk about the neutrons and gammas. I'm sure that you've heard about neutrons in your classes, or you work with them regularly, or maybe you just heard about them for the first time in this summer school. But I know you've heard about them. They were discovered by Chadwick in 1932. And initially, it was really confusing what was going on in the nucleus. But after Chadwick made this discovery, it all made sense that there was this neutral particle in the nucleus. And because it was neutral, it was so difficult to measure. But beyond that, it's pretty similar to a proton. The rest mass is pretty similar, around a GeV or so, a little bit less. It's electrically neutral, and just like a proton, it has an intrinsic spin of 1/2. Gamma rays are similarly electrically neutral, and we use a lot of different terms for photons. If they come over the air and we listen to a baseball broadcast with them, we call them radio waves. If we use them to heat up our food, we call them microwaves. If we take an image with them, maybe of our bones or our teeth, we call them X-rays, but really they're all the same particle. In this case, gamma rays are just photons that come from a nucleus, and they typically tends to be of higher energy than any of the other things I've listed. They have some overlap with X-rays. Gamma rays have no mass, again, no charge, and they have an intrinsic spin of 1. And also, they are the force carrier for the electromagnetic field. So somehow we skip over all of that stuff Kyle talked about yesterday, and we have a nucleus that wants to split into fragments. This could happen because it was induced to do so. So if we hit it with a neutron or a gamma or a proton or a deuteron or any number of other things, anything that makes that nucleus deform enough to fission, that'll do it. There's also spontaneous fission. There are some nuclei that through quantum tunneling processes will sometimes fission on their own without being induced. And the amount of energy released in a reaction like this is around 200 MeV. It fluctuates quite a bit, but it's a good benchmark. And now we are finally at the after. After the scission, the fragments are separate bodies. They're very excited. They have excitation energies of 10 MeV or more, maybe sometimes less. They have pretty high angular momentum. Again, this is just an order of magnitude. They can have quite a bit more, like 4 times more, or they can have even less. And they're moving pretty fast, on the order of 3 to 5% the speed of light. So I'm going to refer back to this diagram a few times throughout the slides. Remember this in your head. We have these 2 axes here. We have excitation energy on the vertical axis, angular momentum on the horizontal axis. And we're going to think of these as resources that are required to emit a neutron or gamma ray. And up here we have a fission fragment that starts out maybe somewhere in this blob. And it has quite a bit of both excitation energy and angular momentum. So the first thing, if it's going to happen at all, it's going to happen now, is neutron emission. Neutrons are generally the emission that take away most of the excitation energy. And that's not just because neutrons have a decent amount of kinetic energy themselves after they are emitted from the nucleus, but most significantly, the binding energy of the neutrons in the nucleus is what contributes. So whenever you emit a neutron from this excited nucleus, you have to first separate that neutron from the nucleus, and that takes a lot of energy, on the order of 6 MeV or so, even with these super neutron-rich nuclei. So every time a neutron's emitted, you take away that binding energy plus whatever kinetic energy the neutron has. The average number of neutrons that are emitted per fission, it depends on the isotope that you're fissioning and how much energy that nucleus had, but it's in the ballpark of 2 to 4 to more. And the average neutron energy in the lab is about 2 MeV for, again, depending on how the reaction started. But for most typical applications like uranium fission, it's around 2 MeV. And this is a pretty fast process. The neutron emission is governed by the strong force, which, if you know anything about the 4 fundamental forces, you know it is, well, the strongest. And therefore, the time scales on which things governed by the strong force operate is pretty short. So this is a 10 to the minus 15 seconds here. Neutrons in fission are emitted in what's often called a Watt spectrum, but really that's just a Maxwellian spectrum that is boosted by the fragments. And I'll talk more about what that means here. So in the reference frame of the fragment. So if you were moving alongside the fragment at 5% the speed of light, you would see that the neutrons are emitted isotropically. In other words, an equal probability in every direction for the most part. And if you tallied up their energies, you would see that it was just a Maxwellian spectrum, just like kind of like a black body radiation, just based on the temperature of the fragment that was emitting them. However, since the fragments are not at rest, but rather are moving pretty quickly, the neutrons also get that boost from being emitted from a moving fragment. And therefore, they're focused quite a bit into the direction of the fragments. And you can see that in the graph here, which is the degree of anisotropy of fission neutrons. Basically, neutrons 90 degrees from each other in a single fission event doesn't happen quite so often. Neutrons that are emitted back to back, however, happens quite a bit, or in the same direction happens quite a bit. That is indicative of the fact that neutrons are generally focused along the fission axis where the fragments are traveling. So neutrons happens first. They take away a lot of excitation energy. You can see we're moving down the graph mostly in this direction. We're losing excitation energy. And you can think of it as a statistical emission, meaning that the neutron energies are kind of random. Now, once it's no longer energetically possible to emit neutrons, like in this case here, we don't have enough energy left to emit more neutrons. We still have to get back to the ground state here, where we have no excitation energy and as low angular momentum as possible. So, and Dr. Ramona Vogt will talk a lot more about this tomorrow. The gamma rays from fission remove some excitation energy, but mostly they remove a lot of angular momentum. And I'm going to classify these into two different categories. There are statistical gamma rays, which kind of perform a similar function as neutrons, and they mostly get rid of energy rather than angular momentum. And then these ERAST gamma rays, which that is not an English word. It means whirlingist, and it refers to gamma rays that come from nuclear states where they are the highest possible angular momentum at a given excitation energy. Then actually that corresponds to this line right here. So if you're along this line, you're on the ERAST line and you emit ERAST gamma rays. Timescale is a little bit longer here, on the order of picoseconds is when that starts, and it'll go until it's done. And depending on the angular momentum of the fragments, you could end up emitting a lot of gamma rays. The average is maybe 6 to 8, depending on the isotope and the energy of that isotope, etc. But I'm showing some nuclear level schemes here. You don't need to pay attention to the numbers, but this is generally just how a nucleus de-excites once it's at the ERAST level. Once you get to this nuclear level, it's a lot like electron orbitals in the nucleus, except, well, it's not electron, it's in the nucleus. So if we're here, we just need to emit these characteristic gamma rays to get to the ground state. So we talked about fission neutrons and gamma rays and about how they have this information about the fragments, the excitation energy and the angular momentum. And in this plot, I've kind of grouped together the neutrons and the statistical gamma rays. So we talked about the neutrons. They have a Maxwellian spectrum, and they're pretty much isotropic in the fragment frame. Statistical gamma rays are not quite like that, but they do have somewhat random energies because the nuclear level density is still pretty high. And they are not quite as angularly correlated with the angular momenta of the fragments. So they're not quite isotropic, but maybe more so than these others, the discrete or ERAS gamma rays that remove most of the spin. These things have well-studied identifiable energies. The nuclear levels in this regime are pretty far apart. So we can catalog these into nuclear data libraries and figure out the energies of each of these. And again, they remove most of the fragment's angular momenta. So they're super important if you want to, for example, do a measurement of the fragment angular momenta. And Dr. Ramona Vogt from Lawrence Livermore National Lab will talk about exactly that tomorrow. So definitely tune in for that. So that's what comes out. But like I've been alluding to this whole time, what the amount and the characteristics of what comes out depends a lot on the fragments that they're emitted from. Now we can have a fission fragment here, but we can also have one here, or here, or here, and how much of this stuff we can emit depends a lot on how many of these resources we have. So if the fragments have a lot of kinetic energy, well, the fragments will be moving faster, and so the neutrons will be more boosted. We might see higher energy neutrons in the lab frame. If the fragments have more excitation energy, then we have more fuel to emit more neutrons. And you can see that reflected in the graph here, where on this axis is the neutron multiplicity, and on this axis is the inducing neutron energy. So as we add more energy to the fissioning nucleus, we start to get more and more neutrons. And you can see it's really significant. We add 10 MeV, we get an entire extra neutron or more on average. If we add more angular momentum, well, we'll probably expect to get more gammas, and specifically more ERAS gammas, since those are the strongest messenger for the angular momentum of the fragments. These are kind of companion plots for that of neutrons here. This was a deuteron-induced fission experiment performed in Norway, where they found a slight dependence on the gamma ray multiplicity, dependence of the gamma ray multiplicity on energy. And this is a plot from our group that sees something similar with neutron-induced fission. So indeed, it appears that there's a relationship as well between how much energy we put in and how many gammas we get. That should be a hint that there's probably a relationship between the excitation energy of the fragments and the angular momentum. We might hear more about that tomorrow. Now, I promised at the beginning of the presentation that we would spend a brief moment on the large timescale stuff as well. So long after the strong and electromagnetic interactions, which are responsible respectively for the emission of neutrons and gamma rays, we also have the weak interaction, well, and tunneling. Many fission products are unstable to beta decay or to alpha decay. And a common example of this is cesium-137. If you've used a laboratory radiation source, you have probably used this one. It's super useful because it just emits one single monoenergetic line. But that gamma ray decay, that 662 keV gamma ray that you might be familiar with, doesn't actually come from the nucleus cesium-137. It comes from barium-137 metastable, and the process is the cesium-137 beta decays into this guy and then decays, emitting that gamma ray. And this is the case for a lot of gamma rays and even neutrons in fission. It's extremely important for controlling reactors, for example. Fission products will decay away, and some of them sometimes will emit neutrons that can go on to cause more fissions in a fission reactor. And the key is that the time scale is long enough that we can implement our engineering controls in the meantime. If not for delayed neutrons, we probably would not have been able to make working fission reactors as soon as we did. And of course, delayed emission is somewhat responsible for long-lived radioactivity of nuclear waste. Now, this definitely doesn't add up to 100 because lots of fission products decay before a half-life of 1 year, but a significant amount lasts quite a while. And that's why nuclear waste is still hot after maybe 10 years. So to quickly summarize, and I want to move into questions you might have, fission is a violent nuclear reaction. It produces fragments with large excitation energy and angular momentum. When we're talking about neutrons, they carry away a lot of the excitation energy, and they're generally thought of as a statistical process. So they have somewhat random energies from being boiled off of that hot nucleus. And they're emitted anisotropically. They're emitted toward the direction of the fission fragments because they're being boosted by those moving fragments. And then, very relevant to the talk tomorrow by Dr. Ramona Vogt, the gamma ray emission carries away a lot of the angular momentum of the fragments. And of course, like we just mentioned, the delayed neutrons and gammas that come from fission and are super important in things like reactors, those come from the decay chains of unstable fission products. And with that, I want to share with you some of the fission research that's conducted at the University of Michigan. These are just a couple examples. When the slides are available to you, these are links that you can click. And with that, I'll take any questions.
Thanks, Nathan. It's always interesting to hear about the fission process. We don't necessarily cover that in all the nuclear engineering classes. It's a very particular subject. And Nathan and his coworkers at the national labs are making a lot of strides in regards to being able to probe these sorts of interactions. But yeah, please do add any questions you all may have to the Q&A. Nathan's subject's pretty advanced, so just general questions on physics are okay too. I know Kyle got a lot of those yesterday. Yeah, and if there aren't anything in the Q&A or you guys don't want to type, feel free to please to raise your hand. I'll unmute you, and you can ask a verbal question. But yeah, if there's not anything to start off, I'll try and come up with one. Sorry, I didn't have one ready to go. But yeah, I don't see anything. So just to give them some time to come up with questions. Yeah, when you talk about fission, gamma rays and neutrons, when we probe for the angular momentum, knowing like how the angular momentum relates to these gamma rays, which I think only the gamma rays are correlated, the neutrons are statistical. So I guess that's my first question. Like, are neutrons from fission, are they related to the angular momentum, or are they purely statistical? And then my follow-up to that would be, if we know how the gamma rays relate to the angular momentum, how does that translate to certain applications? Like, how would that affect our ability to design experiments that utilize the fission process, or design technologies that utilize the fission process?
Mm-hmm. Well, technically, there is still some debate about to what degree angular momentum and neutron emission are coupled. There are some codes that posit that there's a significant amount of neutrons that are emitted in P and D waves, meaning that they have more than just their intrinsic spin. And in that case, neutrons could be responsible for removing a decent amount of angular momentum. I happen to think that's not the case. I think there's some experimental evidence that neutrons are, well, like I mentioned, emitted isotropically in the fragment frame. So I would say they're, at most, it's a small contribution, is my opinion. Regarding gamma rays and their correlations and how they could be used, as I'll give an example for non-proliferation, for example. If we can better understand the initial conditions of fragments through measurements of gamma rays, especially, making a lot of progress in that these days in the field. We can model, the closer we can get to a complete model of fission, the better we'll be able to predict signatures of fission that might not be understood right now. So in the future, we might be able to predict something before it's even been measured, and use that to find illicit or special nuclear material, for example.
Yeah, maybe like plutonium and uranium fragments have different angular momentum characteristics, and you can use those to discriminate between the two. Yeah, that'd be pretty interesting. Yeah, cool. Thanks, Nathan. We've got a couple questions in the Q&A now. John Langley asks, could you speak more to the quantum mechanical processes involved in fission? So quite a general question, but maybe you could touch upon it.
Ooh, involved in fission. Well, let's go here. Yeah, I think this is a good spot. Now, this question is probably much better posed to Kyle from yesterday, maybe too late, or Ramona tomorrow, who is a real expert on this subject. But I think this is a good diagram to look at. So you can think of this diagram just being a scrunched version of this diagram, almost. If you just collapse it along this short axis, you would end up with something like that. But quantum mechanics is the reason that we don't get an even split basically every time. And that's due to nuclear shell effects. Kyle talked about that a little bit yesterday. There are these kind of closed shells that generally form the cores of these of the fission products, and then there's a neck in the middle that quote unquote snaps, and the nucleons in the middle distribute themselves somehow between the cores. If you were alluding to the question yesterday for Kyle about why does quantum mechanics mean that the neck snapping point is random, that's kind of just how it is. Yeah, I'll leave it at that for now. I would encourage you to ask Ramona about that tomorrow if that's unsatisfactory.
Thanks, Nathan. Yeah, that's a tough question. I definitely couldn't answer it. We have another one that asks, oh, well, this should be an easy one for you. Is it true that delayed neutrons sustain the chain reaction in a reactor?
In a reactor under normal operation, yes, they do. If it is just prompt neutrons sustain the chain reaction, then you probably have a reactor that is going the way of Chernobyl. So we don't want that. Yes, reactor operators use delayed neutrons and there we are. Use delayed neutrons and control rods to control the power output of reactors, trying to keep that reactor multiplication just around 1. And again, the key here is that not that the neutrons are different or special, but just that they're emitted on much slower timescales than fission. So every fission generation is, I don't know how long. Flynn would actually be the expert on that, but the delayed emission period is much longer than that, and it gives us time to respond to what the reactor is doing and put in or take out our control rods.
Yeah, thanks, Nathan. Yeah, that's a good question. Delayed neutrons are basically the reason we can have nuclear power plants. Without them, everything would be a weapon. So it's a good thing we have them in hand. William Redding asks about decay chains. Let me see if I can summarize this question. Oh, very specific question about decay chains. He's asking for a technical term for the half-life of a radiation source, including all the stages in its decay chain. And in addition to that, he has to follow up, is there a technical term for this decay chain determination? So basically he's asking you to describe, what is the structure of a decay chain?
My understanding of the question about the technical term is you want to know if there's a term for going from fission products all the way to stable. Not that I know of. I don't know of an industry standard for that term. I will say that usually there's a step in the decay chain that dominates the half-life. So it might be 12 seconds, 13 days, 8 minutes, and then 15 million years. And then you would probably say, you know what, the half-life to stability is 15 million years. And as for what decay chains look like, that depends a lot on where on the nuclear chart you are. Kyle showed a picture of the nuclear chart yesterday with all those different bands of where the nuclei, the closed shells of neutrons and protons are. And generally, if you're neutron rich, you'll probably emit neutrons or beta decay to get rid of neutrons. If you're proton rich, the opposite. If you're just too heavy, you probably emit alpha particles. And there's decay chains can be very long. They're a combination of those things for the most part. And I might have rambled a little bit. Let me know if that's getting at the heart of your question.
Yeah, thanks, Nathan. I think that speaks to decay chains in the context of your presentation. Modu, I would ask for clarity with your question. I'm not sure if this is going to be completely clear, Nathan, but yes, can you explain the gamma-gamma coincidence, which, sorry, I might have missed it in your presentation. For example, the spectrum of cobalt-60, which I don't think would have a gamma-gamma coincidence, but maybe I missed something.
Yeah, I don't think I mentioned gamma-gamma coincidence in the presentation, but you have observed that cobalt-60, there are two gammas that are emitted alongside each other for each decay, or at least each time one's emitted, the other's emitted as well. This isn't one of those nuclei, I think, where you would see it in the lab. This is barium-144, I believe. But if you ended up at this 4+ state somehow, maybe you beta decay into the 4+ state, you would see a 410 and a 258 every single time. And I think that's pretty similar to what you're asking about.
Well, thanks, Nathan. There's another one here. Okay, so we're getting more on decay chains here, so maybe this is the last question. But this person asks, can you explain the process of gamma ray emission in radioactive decay and how it helps identify specific isotopes?
Sure. Gamma ray emission, nuclei that are unstable to any kind of emission generally will eventually undergo that emission. In this case, if we're in this area, there's not enough energy to emit a neutron. It might be unstable to the weak force, but the electromagnetic force is much stronger. If it's unstable to that, we'll emit gamma rays. The way that we can identify nuclei based on the gamma rays that they emit is just like this. If we see a 258, we think, maybe that's, I think this is actually cerium-146 level scheme. So if we see a 258, maybe we think, oh, is that cerium-146? Then if we also see a 410, we're like, this really might be cerium-146. We see a 503 as well, all in that same event. We're probably thinking this is cerium-146. So that's how you can identify a nucleus based on the energy of the gammas. every nucleus will have every nucleus has nuclear levels like this. Depending on how well studied they are, they could have level schemes like this that are available for you to look up and see the different transitions. And these are numbers that are fixed from physics. Like this doesn't change. If it's at 6+ and it goes to this state directly below it in the ground state band, this is going to be a 503 gamma ray every time.
Thanks, Nathan. And then, yeah, a follow-up from William from that original decay chain question. He was actually concerned more about, the question is there an industry recognized verb for the neutralization of radio sources? So we're talking about waste, I think, such that the material has decayed to a safe state of negligible radioactivity.
I see.
I don't know that off the top of my head, so you can try, but
yeah, I'm definitely not in the nuclear waste management field, so that might exist. But I think in order for that to exist, you would have to agree on a metric for what makes something safe, or, well, yeah, definitely agree on a metric on what makes something safe. And if you want to just give a term and not a number alongside it, you have to decide what number of that means safe. And I think you'll find that no one will have the same opinion on that. Yeah, I don't know exactly what you would call waste that is, maybe you're thinking of waste that's ready to be taken out of the spent fuel pool, or maybe you're thinking of waste that's ready to be taken out of the dry cask. Those would be very different degrees of safe, but I don't know if there's a term for that.
Yeah, thanks, Nathan. Well, while you were mentioning that, it did jog my memory a little bit. In the US, at least, there's industry standards for high level and low level radioactive waste. I think there might be some levels in between, but like the Nuclear Regulatory Commission has agreed on how radioactive high level waste is and how radioactive low level waste is. It might not actually be how much radiation it's emitting. It might be more specific to the type of isotope it is. Like actinides are usually higher level waste, and lower level waste might be something like Nathan showed here with the half-lives, something where it's like less than years for the half-life. So you just let it sit in a pool for a little bit, and then it's pretty much just a rock, not radioactive waste anymore once you're done with it. It just depends on how it was processed. There's so many different ways that radioactive material and nuclear material can go through and be processed. And typically once it's stored on site, it's low level waste and fairly mundane. But there's a lot of different hoops and things to go through before you get there. Yeah, I think that fully answers that question. Thanks, Nate, for jogging my memory. That's it for questions. Thanks so much, Nathan, for your lecture today. Always interesting to hear about the multiplicity from fission. It definitely feeds into my work. Oh, William raised his hand. Never mind. We'll give William another chance since we do have time. Go ahead, William. You just need to unmute yourself. Yeah, there you go.
Hello.
Cool.
I just mean to clarify my clarification here. I'm alluding to the questions I asked in the previous lecture about bombarding radioisotopes with neutrons, or as you helpfully pointed me to, gamma particles, photons, basically, to accelerate the process of decay. And that was the context in which I'm asking about these technical terms. I just don't want to put my foot in my mouth and say neutralization when that word means something else in industry.
I don't recall neutralization holding a different meaning. It could be, however, in chemical terms, it could mean something there. nuclear waste is dangerous from a radiological standpoint, but also from a chemical standpoint.
Yeah,
So,
yeah.
there-
And I come from a chemistry background, so that's why I default to neutralization as a term.
Yeah, if you ask us from a chemistry background, we are definitely not experts. So you probably know much more than us, William.
I heard someone once say, if you're a physicist, you might know physics, but you definitely don't know chemistry.
Yeah, it's interesting. I've been listening a lot to the making of the atomic bomb, got the audiobook for it. And quite a bit of the fundamental physicists that started the nuclear industry back in the early 1900s were chemists, physical chemists more typically. But yeah, I couldn't imagine being both. That's a tall order. Thanks, William. And yeah, with that, I think we'll conclude our lecture. Thanks again, Nathan, for coming and giving your lecture. Tomorrow, we will have Dr. Ramona Vogt, and she will be talking about fission again, but more about how we probe this angular momentum in the fission reactions and how we look at the resultant gamma rays and neutrons that Nathan described to characterize these reactions. So it should be quite interesting. Hope you all log on tomorrow, and thanks for joining today. We'll see you.